Okay, here we go again. Welcome back. Welcome back. Before we get started, let me make a couple of comments. Number one, you'll see me coughing. I was coughing before we had this coronavirus crisis. I was coughing in December. My doctor tells me there are lots of people who've been coughing since December. I'm not sick. I don't have a fever. I might get sick. I'm actually kind of half expecting it with the coronavirus, but I hope not. I hope none of you are either. We're going to do Chapter 7 today after we do a little review. Chapter 7 is the one that I compressed because we lost a day of class on the Monday after BYU shut everything down. This is a terrible thing to do, to try to do all of Chapter 7 in one day. I took some more homework problems out because it was even as much as I took out, it wasn't enough. I'm not doing a very good job of telling you how quantum mechanics works, but then on the other hand, to really do it right would take half a semester and a lot more math than you've had yet. So maybe it's okay to do it this way. I hope so. And certainly the homework has been pared down enough that it ought to be fine. Okay, let's do some reviewing about quantum particles. As electrons speed up, their wavelength, what? Their wavelength decreases, and that's because of the de Broglie formula that the wavelength is equal to Planck's constant divided by the momentum. When a fuzzy electron ball in an atomic orbital is detected, so you've seen these fuzzy pictures in your chemistry books. When you detect one of these fuzzy electrons, how does it show up experimentally? How is the electron detected? And the answer turns out to be, it's always a point particle. The electrons themselves are not fuzzy. We're going to talk more today about what they actually are. Those fuzzy pictures just tell you what the probability of finding the electron is. It's not a representation of the electron itself. The nucleus of an atom is smaller than its fuzzy electron cloud size by a factor of which of these? This is worth remembering. It's incredibly small, but I don't know about how incredibly small it is, and the answer is 10 to the minus 5. When electrons go through a crystal one at a time and gradually build up an interference pattern on the screen, the electrons are interfering with what? And strange as it is, the answer is they interfere with themselves. And I can't tell you how to understand that. It's just the way the mathematics comes out, and it agrees with experiments. Okay, so I told you last time that radiation from power lines can't cause cancer, but you know, Brother Higgins died on that power line street in our ward. So let me tell you about that. I get that from my neighbors too, because we have a power line going through our neighborhood, and something like 7 or 8 people along that street got cancer. This has been studied repeatedly in very careful studies, and no link has ever been found. And there shouldn't be a link. The photons from power lines have such incredibly tiny energies that they shouldn't do anything biological. But that doesn't mean there's not a connection. What if the power company used its right-of-way for years to dump PCBs and other toxic chemicals in the soil under the power lines? Maybe back when that area was farmland like it was here in my neighborhood, and then people later built homes there and gardened. Or what if the power lines originally went through farmland? That's our situation. And pesticides got sprayed all over the place, but under the power lines there was never any irrigation to wash them away, and they just built up year after year, and then people built houses and grew tomatoes. Maybe it's that buzzing sound of the power lines. That means ozone is being made. Maybe ozone causes cancer. Well, that could be. Just because you see power lines and you know that there's electricity running up there, don't assume that electric radiation is the cause of whatever the problem is. There might be a problem, but it's probably not radiation. Okay, the wave function psi, you got this in the reading. The wave function psi represents what? And yes, it's the probability of finding the particle somewhere at some time. So this psi thing, it's a strange, strange story. Erwin Schrödinger in the 1920s knew about de Broglie's work and Einstein, and this funny wave-particle waves have particle properties and particles have wave properties. He was looking for a way of describing the waviness of particles. We had a perfectly good theory for the way particles behaved, and he didn't want to lose that, so he wanted to start with what we knew was right, but just make it wave. And so he knew if he was going to make a wave out of these things, there would have to be something that was waving. And so he invented the symbol psi for it without knowing what it was, and then proceeded purely mathematically to try to find an equation that would describe the waviness of these particles. He started with something called Hamiltonian dynamics, which is a fancy version of Newton's laws, and horsing around and using bold guesswork and knowing what experiments and Einstein and de Broglie said, he was able to write down a wave equation for this variable psi without knowing what it was or what it meant. Oddly, even though he invented this mathematical quantity psi and wrote down an equation for it that has worked for nearly 100 years, predicts in great detail what happens in many experiments, he never did figure out what psi meant. And when someone else suggested a meaning for it, namely the probability meaning, he hated it. And Einstein hated the interpretation of psi as giving the probability of finding a particle. And they both hated it until they died. And I don't like it either, but we just don't know what else to do. Schrödinger and Einstein and many others, and there's still people who work on this, they hoped that Schrödinger's wave equation psi would turn out to be something physical, like not probability, but charge density, mass density, energy density, something you could sink your teeth into. But nothing has worked out. And Max Born, a German physicist, was the one who proposed the interpretation, the probability interpretation, that we mostly use today, except for the people who are trying to find a better one. So, proceeding with the standard line, psi as a function of position and time is related to the probability density of finding a particle at position x and time t. It makes it be kind of like those distributions of particle velocities that we saw when we studied ideal gases, or the bell curve that you see, the probability of getting a B on a test, or an A on a test, or a C on a test that you see in statistics. The small probability, dp, doing calculus now, of finding a particle between x and x plus dx, with dx small, is given by dp equals the square of psi dx. Those funny bars on the sides there of the psi before you square it tell you that if it's a complex number, and psi is always a complex number, it has real and imaginary parts, that you have to take the complex absolute value of it first, and then you square it. And probability density is proportional to psi squared. So here's kind of a simple dumb example. Suppose that a quantum particle is confined to the interval 0 to L, and that its wave function psi of x is given by a constant times sine of pi x over L, built so that it goes to 0 at both 0 and L. To turn that into a probability density, you have to square it, and I have tried to sketch what psi squared looks like pretty badly. And that's what the probability density of finding that particle between 0 and L is. So if you ask the question, where are we most likely to find the particle? The answer is, well, we find it up there near the top of the hill at about halfway across the box. If you wanted to know the average position of the particle, then you could use this as a probability density, integrate it from 0 to L times x, and then divide by the integral of the function from 0 to L to normalize it, and you'd get L over 2, just like you'd expect. The particle, on average, is halfway Its average position is halfway between 0 and L. In quantum mechanics, velocity and acceleration are not important at all. We just don't talk about velocity and acceleration in quantum mechanics. There is no F equals ma. It's completely divorced from Newtonian mechanics, except for having a connection with conservation of energy, which came later. The basic building blocks of quantum mechanics are momentum and energy. Schrödinger, because he was using Hamiltonian dynamics, which is based on energy and momentum, he needed the basic physical quantities x, p squared over 2m, the kinetic energy. He needed them to be wave-like. So he invented this funny wave thing, psi, not knowing what it meant. And he decided to do it this way. X, in his theory, position would be replaced by x times psi. And p would be replaced by p times psi. And e would be replaced by e times psi. But to make everything wave properly, he had to make p and e kind of weird. So in Schrodinger's theory, p isn't a number, it's a derivative. So p psi is actually minus I times h bar, Planck's constant divided by 2 pi, times d psi dx. So momentum in Schrodinger's theory is the space derivative of psi, and the energy in Schrodinger's theory is I h bar times the derivative of psi with respect to time. And I, just to remind you, is the square root of -1. So there's imaginary numbers all over the place in this theory. And it just looks like the rage of a complete lunatic. Why would you dream something like this up? Well, here's why. In quantum mechanics, the wave function of a free particle looks like this. It's a constant times e to the I kx minus I omega t. The complex exponential is actually cosine of kx minus omega t plus I times sine of kx minus omega t. And so the complex wave function psi, actually for a free particle like this, actually is just traveling waves. And Schrödinger thought, well, okay, that's what a particle ought to be like. A free particle just moving along, it ought to be a traveling wave. So when you use this for psi, then in Schrödinger's picture, the momentum, p psi, would be this spatial derivative. And if you do that derivative to this, you get h bar k times psi. Well, h bar k, that's de Broglie's momentum, connection between momentum and wave number. So h bar k just shows up naturally. And if you do e psi, Schrödinger's interpretation of energy as a time derivative, if you do that derivative, you get h bar omega. And h bar omega is the energy in the Einstein Planck de Broglie picture. So he got these wave-like quantities of quantum mechanics to show up by doing this funny stuff, even though it kind of made no sense. So Schrödinger went to all this trouble just to get h bar k and h bar omega to show up in place of p and e in his theory. This makes it seem like any old crackpot thing you might feel like inventing would get you a Nobel Prize too. But the problem is that your crazy theory has to agree with experiments. It has to agree with lots of experiments, year after year, probably for a decade. And it's a pretty high bar for him to have something crazy pass. And somehow, Schrödinger's theory passes this bar. Okay, well, what about kinetic energy? What does kinetic energy look like in quantum mechanics? Well, kinetic energy is not 1/2 mv squared because v doesn't show up in quantum mechanics. Energy is p squared over 2m. That's the momentum way of writing the kinetic energy. Since it's p squared, that would be taking p twice, which means take 2 derivatives instead of 1 derivative. And if you work all that out for a moving particle, you get h bar squared k squared over 2m psi. Exactly like it ought to be. It's the quantum mechanical p squared over 2m. So kinetic energy is the second derivative. Momentum is the first derivative. Total energy is a time derivative. And this is how Schrodinger then proceeded. He took energy conservation, p squared over 2m, plus u of x equals E. That's conservation of energy. You rewrite it in his funny quantum language by putting these psi's in here. And then you replace P and E with derivatives in space and time. And you get this equation. This is Schrodinger's equation. And if you've had enough mathematics, you'll realize that that's a kind of a wave equation. It's got spatial derivatives and time derivatives in it. This is this is the partial differential equation that describes waves. And so Schrodinger's equation is actually a wave equation, and its solutions turn out to predict all kinds of quantum phenomena. Well, if you do something crazy like this, it either turns out to be useful or it doesn't. And it does. It predicts energy levels in atoms. It predicts energy levels in nuclei. There was no idea before these kinds of theories came out that such a thing even made sense. It predicts them and gets the numbers right. It predicts that there are vibrational levels in molecules. It predicts the details of radioactive decay. It predicts what happens in semiconductor electronics and superconductivity and on and on and on. So it's a pretty powerful theory. Let's see if we can get at least a little bit of a feel for how it works. So consider a particle confined to a cubical box of side length L. It's got no potential energy, and the potential energy inside the box and the potential energy at the sides of the box is infinite, which makes it impossible for the box to escape. So we take Schrodinger's equation, we look for solutions that look like standing waves. Those are the solutions that give you energy levels in these systems. So we look for a standing wave solution, so some function of space, f of x, y, z, times a function of time. And because it's quantum mechanics, we always choose e to the minus I omega t. We don't pick cosine omega t or sine omega t. In quantum mechanics, you always pick e to the minus I omega t. You take Schrodinger's equation, you put this guess for what it looks like in, and you get this equation at the bottom, which has spatial derivatives in it, and then some constants. And the energy shows up. Well, you can solve this equation by guessing that the proper functions are sine functions. The question mark on that equal sign means you guess that it looks like this, you put it in. If it works, then you say hooray, and if it doesn't work, then your question mark was answered in the negative and you try something else. Well, you put this in, and it does work, and it gives a formula for the energy E as a function of how wiggly the sine functions are in the x, y, and z directions. The energy is h bar squared pi squared over 2ml squared times L squared plus M squared plus N squared. And each one of those integers tells you how many wiggles there are in either the X or the Y or the Z directions. The lowest energy, we call it the ground state, is when each one is 1. And the larger integers give the excited states, like 121, 132, 579. Pick anything you like, and as the numbers go up, the energies go up. And that's normally the case. As the wave function becomes wigglier and wigglier, the kinetic energy goes up. Well, this simple formula roughly predicts the energies that electrons and protons and neutrons have in the regions that they're confined to. So an electron is confined to a region about 2 times 10 to the minus 10 meters wide. If you just use this simple particle in a box formula, which isn't right, and put 111 in it, it predicts that you have an energy of 28 eV. You get EV-sized energies, which is right for atoms. That's how big the energy levels are. They're EV-sized in atoms. In a nucleus, which is way smaller, that L in the bottom of the energy formula, after you square it, makes it be enormous. And so instead of EV-type energies, like you have in atoms, in a nucleus, you get mega electron volt energies. And Schrodinger's equation predicts this and gets it about right. Okay, so you can get energy levels. What does it mean? If I give you a chi-squared function, this probability function, it's that red blob, you would be perfectly justified in asking, hey, where's the particle? Where is it? And the answer is, well, until you detect the particle, it's everywhere between 0 and L, simultaneously. You can't tell where it is until you detect it. It has the highest probability of being found at about L over 2, and no probability of being found right near the edges of the box. But until you detect it, you don't have any idea where it is. Which then leads us to the idea of Schrodinger's cat. Schrodinger didn't like his theory, predicting that the particle is everywhere. So to make fun of his own theory, he invented Schrodinger's cat. He said, suppose that a cat in a box, which you can't see in this box, it's all sealed up. You have a cat in there, and suppose that cat can be described by a simple wave function with only two states. The two states are dead and alive. Those are the two possibilities for the cat. Schrodinger said, if you believe that this wave function of mine says that the particle is anywhere in the box, then that would predict that the cat is both dead and alive. And that until you look in the box, you can't tell whether the cat's dead or alive. It's both dead and alive until you look in the box. We are forced to say, if we believe Schrodinger's theory, which he hated, we're forced to say that the cat is simultaneously dead and alive. You can even find posters about this. You can find t-shirts that say this. Now, one of my kids gave me this poster for Christmas. Well, Schrodinger's cat, of course not using a cat, but using photons in quantum states that are simultaneously either spin up, and spin down. I almost said either. No, it's not either. They're both. This photon is both spin up and spin down until you check it somehow. The predictions of Schrodinger's theory for quantum states of photons that are simultaneously up and down have been verified over and over and over again. It's called quantum entanglement. It makes everybody's head hurt, but it's called quantum computing, and it might change the world, again, just the way normal digital computing did, which is pretty straightforward and makes sense. Quantum computing is crazy and very powerful, and it might change the world again. But no, you cannot use it for faster than light speed communications. You'll find lots of talk about this on the internet. It doesn't work, but you can use it to solve computational problems that would be impossible with an ordinary computer. So let's review a little bit. If a particle is confined to a small box of side length L, then the uncertainty principle says that the momentum of the particle must be what? You remember the uncertainty principle, right? That's actually built into Schrodinger's theory too. Schrodinger's theory predicts the uncertainty principle. You don't have to just state it. It comes out of the theory. It's very natural. And the uncertainty principle, which is that L, the size of the box the particle's in, times its spread in momentum is bigger than h bar over 2, that actually predicts that particle momenta in a confined region ought to be on the order of h bar over L. Just divide the uncertainty principle by L, and you'll see an h bar over L on the other side, and forget about the 2. The momenta ought to be about as big as h bar over L. And you can predict the sizes of energy levels in confined systems just by using the uncertainty principle. The units of h and h bar are the same as the units of what? Well, it's momentum times length. You can tell that from the uncertainty principle. You have a momentum times the length on the left side, and you have h bar on the right. It's also energy times time, because the uncertainty principle for energy and time is energy delta E times delta T is bigger than or about h bar over 2. So that works too. That turns out also to be the units of angular momentum. That's a momentum times a lever arm. So that has units of momentum times length. And angular momentum is quantized in quantum mechanics. So h and h bar have very interesting units. In quantum mechanics, momentum and energy enter the theory as what? We did this a minute ago. See if you remember. They come in as derivatives. Momentum is a space derivative, and energy is a time derivative. In quantum systems, the energy levels are obtained by looking for solutions of Schrodinger's equation that are what? Well, they're standing waves. And those fuzzy electron ball pictures in your chemistry book, when we do the next chapter, chapter 8, I will show you that those are in fact standing waves. Standing waves of what? Standing waves of psi. Schrodinger's mysterious waviness property. Those pictures in your chemistry books are standing waves of psi. All right, now there's another topic we should talk about. It's called quantum tunneling. If you think about it in particle language, it's very mysterious, but if particles are waves, then waves really ought to do this. It's simply reflection and transmission. That's what waves do. And if a particle is a wave, then it ought to do something like reflection and transmission. And so the way it works is that potential energy changes act like indices of refraction. They change the wave speeds. And so when you have a change of index of refraction, as we learned for light, some of the light is reflected and some of the light is transmitted, unless you have something crazy like total internal reflection. But under normal conditions, some waves reflect and some are transmitted. And it makes perfectly good sense for waves. You see it every time you adjust your tie before you go into a meeting, for you young men, using the window on the side of your car. Someone inside the car could see you, which means that the light from your face is going into the car, but you can also see your reflection in the window, and you can use it to fix your tie. I suppose women must fix something too, when using the windows in a car. What do you, fix your hair or something? I haven't done it, so you'll have to tell me. So this is perfectly natural for waves, but it's crazy for particles. But if particles are waves, then they ought to do this, and they do, and it's observed in experiments. So let me take you through this a little bit by doing little simple quizzes. Suppose you have 1,000 Newtonian particles, and you shoot them at a potential energy hill that they have enough energy to get over. What do the particles do? Well, if they're Newtonian particles, and they have enough energy to go over the hill, they will always go over the hill. That's the correct answer in Newton's world. If you shoot 1,000 quantum particles at a potential energy hill, and they have enough energy to get over, they don't do what Newton says. Instead, they sometimes go over, and they sometimes come back. Sometimes they're transmitted, sometimes they're reflected. Suppose you have a potential energy hill that the particles can't get over. What happens then? Well, in Newtonian physics, they can't get over the hill. They go partway up the hill, they stop, and they come back every single time. If you shoot 1,000 quantum particles at a potential hill that they can't get over, that they don't have enough energy to get over, what happens is, well, they usually come back. But once in a while, they appear on the far right, having tunneled through this potential energy barrier. So here's a very, very bad sketch of what the wave function psi would look like for tunneling. So the red wave on the left is the incoming wave, representing particles coming into this potential energy barrier from the left. When the wave gets to the potential energy barrier, it can't propagate inside the barrier, it doesn't have enough energy. But that doesn't mean that it completely quits. It means that the wave function dies slowly, has an exponential decay inside that red region where the potential energy is too high. The green wave is the reflected wave, but on the back end, if the potential energy hill doesn't extend too far, then the particle can be reborn in a region where it does have enough energy to propagate, and you get a red wave again on the back end of the barrier. This is also what waves do. Waves can propagate through regions that they are not supposed to go through if they're not too thick, and then they can escape out the back end. Let's go revisit kinetic energy again. Because you have a homework problem on this, I want to make sure you understand this. Kinetic energy is the second derivative of the psi function. And so second derivative, if you remember from calculus maybe, is curviness. And so the first curve there shows something with not very much curviness. The bottom picture has lots of curviness and therefore has much higher second derivative than the first one. In quantum mechanics, the bottom one would have lots of kinetic energy and the top one wouldn't have very much. So that particle box example, in a box example in the book, remind you of the formulas again. Those integers there, L, M, and N, they tell you how wiggly or how curvy the wave function is. And so it makes sense, as those numbers go up and the wave function gets curvier and curvier, that the energy gets bigger and bigger. So here's an example of a high energy state for a particle in a box. It's L equals 3, M equals 2, and N equals 1. It's got lots of wiggles, and it's got high energy. Here's the low energy ground state of the particle in the box, the 111 state. And this is important, these ideas of high energy states with lots of wiggles and low energy states with not very many wiggles. That's important for the way bosons, like photons, and fermions, like electrons, behave. If you're a boson, then you're very social and you want everybody to be in the same quantum state. And so if you had a bunch of photons living in this particle in a box potential well, they would all want to be in the ground state. Now, you might have enough energy in the system, maybe because it's connected to something hot, that some of them would be bumped up into the higher energy states, but where they really want to be is in this bottom state. Everybody likes to be in the lowest energy state, right? Well, for electrons, it's a little complicated. Electrons are fermions. They're antisocial. You can only get 2 of them in this state. You wonder, well, why 2? Why not just 1 if they're antisocial? Well, electrons have spin, and we'll talk about that in the next chapter. And so you can put a spin-up electron and a spin-down electron in one quantum state. But you can't put any more than that. This ends up being enormously important. We live in a low-temperature world. It's just not very hot here where we live. And at this low temperature, if all the particles in the world were bosons, then they'd all be pretty much in the ground state. Because fermions don't want to go into the ground state, if you have a bunch of fermions in a quantum system, you'll have 2 in the ground state, but if you have 8 more, the next 2 have to be in the next highest energy level up, and the next 2 after that have to go into an even higher energy state. And this filling up of the energy levels, higher energy levels at low temperature with electrons is what makes the whole periodic table possible. If electrons were bosons, there would be no chemistry, there would be no biology. So if you're ever lucky enough to get to design a universe, you want to make sure that you have lots of fermions hanging around and not just bosons, because it'll be a very boring world if you don't. All right, you have some questions for next time, and I look forward to meeting with you in this odd way again sometime soon.